Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Today we're very happy to have Leo Raisin here visiting us. He's a professor at BU and he's done a lot of work on things like extraction and key agreement and leakage resilience and a whole bunch of other things. And today he's going to be telling us about some notions of entropy and applications to key agreement and leakage resilience.
Thank you, Melissa. Thanks for inviting me. So entropy that I'm going to be talking about is sort of a thread that ties everything together, but that doesn't mean that I don't want to tell you about the parts that it's tying together. So feel free to ask questions about any of this. I want it to be interactive, and there are different pieces that I'm trying to fit together. We'll see how well it works. Let's see. What's the magic? Okay. So there are many, many ways to measure entropy. You may have learned some of them in some of your classes. There's the classic Shannon entropy. That's not the one I'm going to talk about. So if you don't know what it is, you're safe. If I want to just, I'm the bad guy. I want to guess your password. Obviously, your password has to have high entropy. But from what point of view should it have high entropy? It just should be hard to guess, right? That's really what we mean. So we will try to define entropy throughout this talk as the probability that the adversary predicts a sample from your distribution, right? So you have some distribution we're talking about, and you look at the probability that the adversary will successfully predict a sample on one attempt. And then, well, that probability is going to be obviously less than 1, so in order to make a log positive, we're going to have to take a negative of the log. That's just the way you always deal with entropy. You have to take the negative log, right? But if the probability is to the negative 80, then you have 80 bits of security. That's sort of the idea. Yeah?
Usually for Min-Entropy, there's a max operation. Why the max is not here?
I'm sorry?
Usually for Min-Entropy, it's minus log max.
So I'll show you in a minute. But this is the right. I'll write the formula in a moment. But I want you to think of this as the philosophy behind everything I'll talk about, because there won't be just one definition. There will be many, but they will all be about the probability that the adversary predicts a sample. Okay, so that's the important part. We want that probability to be small for obvious reasons, right? Like passwords. Okay, so far? Yeah, wanting it to be small? Good. So now if I actually draw a distribution, and capital letters, I'll try to be consistent. Capital letters will denote distributions. Lowercase letters will denote samples from those distributions. If I have a distribution of passwords, and you're the adversary, which one are you going to go for? If you're moderately smart, you're not going to go for this one, you're going for this one, right? You're going to go for the most likely password. So I take the maximum probability event over all possible events in my distribution. I take the negative log of that. That's the min-entropy. That's the definition of min-entropy. So it's a very, very simple definition. And the reason it's called min-entropy is because if you took the max outside of the minus sign, you would have a min. Yeah? It's just a silly thing. Okay. So that's min-entropy, and that's been around for a very long time. So what is it good for? Well, so one, I already talked about passwords, right? If you have a password, it better come from a low min-entropy distribution. High min-entropy distribution, right? If you have a password and you want, sort of 80 bits of security, then it should come from a distribution with min-entropy 80. So the maximum probability should be to the negative 80. What else? Well, it turns out it's good for message authentication. This was observed some time ago by Renner and Wolf. So let's say I have a key that does not come from a uniform distribution for whatever reason. I can't sample things uniformly, right? And I want to use that key as a message authentication key, so that you and I share that key, and it's a symmetric message. And I want to send you a message using that key. So the way I'm going to think of this key, it's going to be of length n. I'm going to split it into two parts of length n over 2 each. Each of those halves, I will think of it as being in the correct finite field. And here's my message m. And I'm going to think of it as belonging to the same finite field, right? So key is twice as long as the message in this case. And I'm going to multiply it by the first part. I'm going to add the second part. And that's going to be my message. That's going to be my MAC, right? My tag on the message. Okay, so it's A times M plus B. Have people seen this? How many people have seen this MAC construction? I'm curious in the audience. Okay, so not everybody has seen it. So this is a MAC construction that actually goes back to Wegman and Carter, all the way back to 1981 when they talk about universal hashing. There's a first paper of Carter Wegman, universal hashing for algorithms and data structures purposes, and then they realized 2 years later that the same tool that they already developed actually works for security. And this is a message authentication code. So it turns out this is secure if A and B are chosen completely uniformly at random. This has nothing to do with entropy, right? This is just uniform random key. This is going to guarantee that any adversary who sees sigma and M cannot modify the message and come up with a different sigma that verifies correctly. Right? But what if we don't have full entropy, right? What if we only have some k bits of entropy in here? Right, so think of the entropy is somehow distributed through this AB. It's not like certain bits have entropy and certain ones don't, but I'm going to draw it like this so we can visualize it. Right? So imagine that all the entropy is sitting in B, and then there's some also sitting in A. And so the gap, the lack of entropy, which I'm going to denote by this sort of brick color, is n minus k, right? That's what's missing. It turns out that this thing is still secure, and the amount of security you get is what's in this sort of bricked off area. That's your security. The security is the difference between n over 2 and the entropy gap. In other words, what is this really saying? It's saying that you better be at least half entropic, right? And essentially there should be some entropy in A and some entropy in B. Because if either component has no entropy, then you clearly didn't need such a complicated function. You could have done without it. So this but it says that if both components have enough entropy, this is going to work. I'm not going to prove this result. Just
that's for that specific.
That's for that specific MAC. Okay. In fact, later I'll show a result that says that this is essentially the best you can do. If you have less than half entropy, then message authentication is not possible. So if you and I share a key whose entropy is less than half of its length, we cannot authenticate a message without somehow coming up with more shared randomness. This key alone is not enough. Okay.
Does it imply that you have good entropy and somehow shorten the key length in practice?
So it would be nicer, right? It would be nicer if the key has entropy k, it would be nicer if it also had length k. You're sort of wasting all these g bits, right? But we don't have a nice generic way to shorten the key. So it's best to have keys that have full entropy. Still the case. It just says that if you don't quite have full entropy, if you're worried about not having full entropy, you may still be okay. Does that make sense? Yeah, and this holds only with respect to min-entropy. If you have a different notion of entropy, it's not clear that this is going to work. And there's a proof of this in Maurer and Wolf. I'm not going to prove it here. So does it make sense what I mean by security here? What do I mean by security? Right, the game is no. So please ask. Okay, so the game is you and I share this key. I want to send you a message, and Kristen wants to mess with it. Okay, so I send you the message, and she sees the message and the signature sigma on the message. She doesn't know the key. She wants to modify the message and the signature so that you still think it's okay. And the way you're going to verify is by computing the same formula and seeing if it matches. Right? And then the point is that it's not going to be possible, and it's not going to be possible exactly with this probability. The probability of success is 2 to the minus this. So this is the amount of bits of security you get.
What's the name of that paper?
This Maurer-Wolf paper, I think this, I'll have to look it up for you. I think it's in their information-theoretic, I think it's in their privacy amplification paper, but I'm not sure.
So this is an information-theoretic result?
Yes. All the results so far are information-theoretic. There's no computational assumptions we're making, right? We're not assuming hardness of anything, just assuming entropy of keys. Other questions? No? Good. Okay. So what else is it good for? So this is the MAC. I just want to keep it up there. It's also good, it turns out, for secret key extraction, provided we have something. And I'll tell you exactly what I mean by have something. But once you extract a good secret key that has full entropy, then you can use it for one-time pad encryption. If you believe in hardness assumptions, you can use a pseudorandom generator to expand it out. You can use all sorts of things, right? And so secret key extraction seems like a nice thing to have. So what do I mean by secret key extraction? There's a primitive called an extractor that'll take an input that has reasonable amounts of entropy. It'll take a uniform seed, and it'll output something that is uniform. Okay. How many people have seen extractors? Yes, almost everybody. Okay, good. So this seems like cheating because I have to give a uniform seed to get a uniform key. So kind of what's the point? If I could have done, if I could do that, then why do I need this thing for? But it's not cheating in the following sense, in the sense that the seed and the output will be jointly uniform. This is known as a strong extractor in the sort of the old classic literature. What does that mean? That means that any adversary who sees the seed still doesn't know the key. Right? Or any adversary who knows the key doesn't know the seed. And so they jointly distributed almost uniform, epsilon close to uniform, whatever epsilon you want to set. And that essentially means that the seed can be reused like a catalyst in a chemical reaction. Right? So what's a catalyst? You throw it into a chemical reaction, reaction happens, you take it out. And you can throw it into the next chemical reaction. It's the same thing with the seed. You need a seed. You need to throw it in order to extract a good key, but the seed is reusable. In particular, it can be public. As long as it's uniform and independent of this W, you're okay. Right. So that's the important feature of extractors, that they do need a uniform bits, but those bits can be public and reusable, as long as they're independent of whatever input to the extractor you have. Right, and in some constructions, good point, Shweta, right? In some constructions, the seed can be much shorter. The seed can be logarithmic in the length of this and the length of this. It could be really, really short. Although actually, we won't be taking huge advantage of that fact here, but it is a useful feature. Like you need very little uniform randomness, and then you can extract a lot. Okay. So this is reusable. Extractors go back, to the mid '80s, although they were not formally defined until mid-90s, really, but we've seen them. We know them from then. Okay, so I just want you to remember that those are three things that MinEntropy is good for already, without any extra work. None of it is my work here. But then you could ask, what about private simplification? How many people know what private simplification is? Good, so I'll define it then, since we don't have a... Okay, so private simplification is the following thing. Alice and Bob have a shared W. This is, think of the scenario of message authentication that I was talking about before. It's the same scenario. You and I share a secret key. And our adversary knows something about it. Okay? And because the adversary knows something about it, it's no longer fully secret. It's partially secret, perhaps, because the adversary might not know everything about it. So a classic example is, there's several classic examples. A really classic example going back to the 80s to the original motivation is quantum key agreement and quantum key distribution. Bless you. If I said things over a quantum channel, the adversary may eavesdrop on some of them, but not too many. So the adversary may eavesdrop on some bits that I sent without modifying them, but after a few, there's a good probability that they become modified and we detect it. That's essentially what's going on. So the adversary knows something about our shared key, but not everything. There are more motivations today. Sort of people are trying to do key agreement where, we take two cell phones and we shake them together. The cell phones share some common information W about the way they were shaken, but it's hard to argue that the shaking pattern is fully secret. It's somewhat, it may be partially secret, but there's some base pattern that is probably the same for every shaking. So there's sort of some notion of entropy, right? That Alice and Bob share some entropy in this key that nobody else has, but it's really hard to, pin it down and know exactly what Alice and Bob share. Okay, so that's the scenario of private simplification, and the goal is to agree on a uniform secret R. Because why? Because once we agree on a good uniform secret, then we can use it as a one-time pad, as a pseudorandom generator, as whatever. Right? So this is sort of the start of all cryptography once you have a uniform secret. So that's the goal. The goal goes back the first sort of a non-constructive construction of Ozarov and Weiner, right? Non-constructive construction. It's sort of existence proof, and then back in '84. Okay, and the simple solution, given sort of the terminology that we have today, is to just use an extractor, right? Alice can generate a random seed I, send it over to Bob. We don't mind that Eve also gets I in the process, because we don't mind that the extractor seed is public. That's the beauty of extractors, right? and then Bob can do the same thing. Right? So this makes sense. It's secure against Eve, who eavesdrops on the channel and knows something about W. It seems to work, except, in order for extractors to work, you have to know the entropy of what you're extracting from. You certainly can't extract more than the entropy you have. Extractors are designed to work for specific entropies. Well, how do you know the entropy you have? The entropy you have depends on Eve's knowledge, and we're going to use Y to denote Eve's knowledge. Right? So in order to know what extractor to apply, it would seem like we have to use we have to know the entropy, and we may not because it depends on what Eve knows. So it seems like min-entropy is not good enough anymore. So let me talk about a different definition, a conditional definition of entropy. Let's think about it for a moment. So imagine that what we have is a uniform key initially, perfectly good uniform key. It's not like we are unable to design, generate uniform bits. It just so happened, however, that Eve, through her devious ways, found out the Hamming weight of our key. The number of ones in it, right? So let's think about the entropy. Well, let's say that Eve knows that the Hamming weight is exactly n/2. Half the bits are ones. Y is the knowledge of Eve. So let's say that Eve's knowledge is this. The probability of this fact happens to be that. There's a bound. Okay, just trust me on the bound. Okay. Well, if that fact is not terribly surprising, 1/2 roots n is not terribly surprising. So Eve's knowledge is not a lot, because you know a lot when the knowledge is surprising. Yeah. So because of that, we could prove, this is a fairly straightforward proof, that the entropy of the original key, conditioned on Eve's knowledge, this is Eve's knowledge, is what it was originally, minus the log of this. And the log of this is half log n minus 1, or half log n plus 1. Right?
Does this always hold, or does it only hold with high probability?
If I tell you that Eve's knowledge is x, then my probability reduces by, my entropy reduces by log of x. That's a fairly straightforward thing to prove. Does that make sense? So if Eve's knowledge is, so this is the easiest to imagine condition is suppose Eve knows that the first bit of a message is 1. Then her entropy got reduced by 1 bit, because the probability of that fact is a half. It is. For min-entropy, it also works. It's actually, for min-entropy, it's even easier to prove. Because you just look at the conditional probability, it cannot jump by more than the probability of the condition. Min-entropy is about the max. The max cannot increase by more than the probability of the condition, because the way conditional entropies behave.
Inequality here is coming from the bound, not from the chain rule.
Inequality,
Inequality, like when we say h infinity w given y is greater than n minus whatever. So the greater than equal to is because of the inequality on the...
Oh, I see. If this was equal, would this also be equal?
Because it sounds from what you said that you can say that h infinity of w given y is min-entropy of w minus min-entropy.
No, actually, so no, it could be better. The entropy doesn't have to get reduced by that much, because the probability of the... It could be that if w wasn't initially uniform, there are examples. So imagine the following example. W wasn't uniform initially. W has the first bit always equal to 1. And Eve finds out that the first bit is equal to 1. Well, she hasn't learned anything new, so it doesn't reduce the entropy. So you don't necessarily get equality. Okay, so that's if Eve knows that the Hamming weight is exactly half, which is the most likely Hamming weight for a given string. But if Eve knows that the Hamming weight is n, well, that's a very, very unlikely event, so she suddenly learned a lot, right? The string is all ones, so the entropy is gone to 0. But, sometimes you don't want to reason about the sort of what if Eve knows this or what if Eve knows that. You just want to say, conditioned on the knowledge of the Hamming weight, do I have entropy or not? So you really want to sort of talk about the average, in some sense, conditioning, right? Not conditioning on the worst case, not conditioning on the best case, but conditioning on the typical case that happens. How can you even talk about it? Well, you can still try to do the same thing. Remember that min-entropy is the log of predictability. You can still ask, run the whole experiment, and ask what is the probability that Eve predicts my sample. So what is the experiment? The experiment is I pick a random W, I give Eve its Hamming weight, and Eve is incredibly smart, all-powerful. I ask, given that she knows the Hamming weight, what is the probability that she predicts my W? It's a meaningful thing to ask. And so that's what we want to define, the probability of predicting W given Y, as our entropy. And it turns out that the right thing to define is the expectation over all possible Y's of the maximum of the probability that W is that for a particular Y, right? So whatever Y Eve knows, whatever particular value of Y Eve knows, she's going to go for the most likely W. So if she knows this, if she knows the Hamming weight is this, she's going to go for this W. If she knows the Hamming weight is that, she's going to go for that W. Right? But she doesn't control the Hamming weight. I choose W initially. So this is expectation over all Y's. It's not the worst case Y. She doesn't control that.
Why would
Dave?
you try to pick, repeated samples until you get one that will be optimally good for you, given that you know even
So often you don't have the luxury of picking repeated samples. Let's say you shook your phones. You don't want to tell users to shake phones a million times, right? And often you don't know that Eve knows the Hamming weight. It's very hard to sort of bound exactly what Eve knows. You're just going to make assumptions, something like Eve knows no more than some number of bits, and hope that you're right. Right? I mean, if this is too clean an example for real life.
But if we're willing to make this assumption, and you could resample, then
Right, then I would just sample if I know that Eve gets the Hamming weight, I would sample things of Hamming weight full.
Sure.
Or Hamming weight half, and that's it. I would not even bother. Right? But yeah, sometimes I don't have that luxury. So Y is some knowledge of Eve. It's a random variable that's correlated with W. So W and Y are correlated random variables.
Like it's
Yes.
just a random variable with some distribution.
Exactly. So Y and W are correlated random variables, and you can define this notion. And so this was defined by Doris Ostrovsky, myself, and Adam Smith way back in 2004 as we call it, I think, average conditional entropy or something like that. And then, of course, at the end, you have to take the negative log, as always, because when you talk about entropies, you take logs. Just easier, so you don't have to deal with really small numbers. Notice that average min-entropy is not the average of mid-entropy. The expectation lives inside the log, not outside the log. Makes a big difference, so a good counterexample to consider. Imagine you have a system where for half the cases mid-entropy is 0. Eve knows everything. And for half the cases mid-entropy is 1,000. What's the probability that Eve guesses? It's about a half, right? So you don't want to average 0 and 1,000 and get 500 bits of entropy. You don't have 500 bits of entropy. If half the time you have 0 and half the time you have 1,000. Shannon entropy doesn't behave this way, right? In Shannon entropy, for those of you who know Shannon entropy, if half the time you have 0 bits of Shannon entropy and half the time you have 1,000 bits of Shannon entropy, then on average, Sharon says you have 500 bits of entropy. You don't here. Not from a security point of view. And if you sort of look at a lot of older papers doing the kinds of stuff I'm talking about here, they consider Shannon entropy because they didn't have min-entropy to talk about. And they would prove things like the resulting key has 500 bits of Shannon entropy. Well, that's not interesting. 500 bits of Shannon entropy means it could be 0 half the time. That's not good enough. And so really it took a while for people to converge to better notions of entropy than Shannon. So take the log after you've done everything. That's the moral of this. Does that make sense? Yeah, so, okay. Right, so for any pair of distributions YW, I can specify min-entropy. I can measure. Of course, if I don't know anything about the distributions, then it's bad. So I'll give you examples. I promise. So, okay, so now we have this average min-entropy. And we can ask the same question, what is that one good for? We had the original min-entropy, what is this one good for, the average case? You can still prove essentially directly from the definition. If you have an adversary who knows Y, and your password is W, then the probability of guessing it is exactly to the minus entropy. And if you think about it, this is a better way to model passwords. The adversary knows something about you. That's the Y. You pick a password, that's the W. It's always conditional. Life is never sort of you live in a vacuum and there's no information that the adversary has. So this is really the right way of modeling a password. There's a W that you know, there's a Y that adversary knows, and they may be correlated in some way. The adversary may know your gender, age, birth date, whatever, right? That's the correlated stuff. Turns out that the same message authentication code that I talked to you about earlier also works for average entropy. Right. The probability that, I think Kristen was our adversary, the probability that Kristen will be able to modify the message and the signature and it'll still verify is exactly, is exactly 2 to the, whatever it was before, except you substitute average entropy for the true entropy, which is nice. And the nice thing that was proven by Salil Vadan just like 2 months ago, literally, is that every extractor that works for entropy also works for average entropy. I think with a loss of 3 bits or something like that. But essentially, yeah, 3 is an actual number. I'm not exaggerating. This one, whatever I just defined, I call it average entropy, or people call it conditional entropy. I don't know, but I think conditional min-entropy is probably the right notion, the right way to call it. So Salil proved, we knew before that some extractors worked and some worked with a fairly big loss, and Salil proved that no loss is needed. Essentially, you lose 3 bits and that's it. So all extractors will work for this notion. So, right, this whole thing. And so what I mean by all extractors work, I mean that the output of my extractor will look uniform even to the adversary who knows why. And so there's an adversary who has this additional information. The output will still look uniform even to that adversary. It will be statistically close to uniform, even given that extra information. So that implies that privacy simplification works. Remember what motivated us? This question of Alice, Bob, and Eve, where Alice and Bob share some W and Eve knows something about it. Now, finally, we can say that we can put a rigorous condition on what we want in order for privacy simplification to work. What we want is that the conditional entropy of the W conditioned on Eve's knowledge should be high. And if it is, then we're good. Then an extractor will work. David?
But you still have to sort of say, I believe Eve only knows why and not some other distribution.
Correct. Yes. You have to say, and I'll show you how to bound that, how to be able to say that in a moment. Yeah.
Does this require like a large number of trials?
No repeated independent experiments at all. So if you and I share a W, and we're worried that, who's going to be the next adversary? David. We're worried that David knows something about our W, but we believe that there's some entropy left in W conditioned on his knowledge, then we're okay.
This setting,
Mm-hmm.
this setting reminds me of the sort of work of password authenticated key exchange.
Mm-hmm.
Sort of, is it exactly the same setting?
It's the same setting, except in password authenticated key exchange. So W is the shared password. Think of this as the client. That is the server. They share password W. In that setting, they don't mind making computational assumptions.
I see. Oh, okay.
This is information theoretic for now. Right. So the first half of the talk is information theoretic, and then we'll see how far we get into computational. So password authenticated key exchange also solved this problem. The nice thing about this is this can be very efficient. Extractors can be incredibly efficient constructions. Some dot product, that kind of stuff. No fancy math required. Okay.
Does Vadan's theorem, is that only when you're talking about Eve knowing the Hamming weight, or does it also work like if she knows some other stuff?
No, so the statement, the rigorous statement, well, as rigorous as I'm going to make it on a slide, is this: if the conditional entropy is equal to k, then for some k, and the extractor was designed for that specific k, then the output will be jointly uniform. So for any y, not just Hamming weight. For any y, as long as the conditional entropy of W conditioned on y still remains high. Right. So if you look at extractor literature, it says this extractor will work. This is a k epsilon extractor. It means it works for anything with min-entropy k. And Salil proves that essentially, if it was a k epsilon extractor for unconditional entropy, then it's also a k epsilon extractor for conditional, or maybe k plus 3 epsilon, something, But,
So this extractor.
Mhm.
So this single extractor will work for a large number of distribution for y as long as.
Exactly. No matter what y is, as long as W has entropy conditioned on y.
And in particular,
Mhm.
does the theorem work even if you don't happen to be able to sample from Y or be able to decide membership?
Y doesn't have to be efficient in any sense.
Okay, great.
It's all purely information
That's
theoretic.
pretty cool.
It's really cool. Yeah.
Yeah.
And moreover, it's like a page and a half proof with all the details, so it's nice. So yeah, it's in. I can find a pointer if you're curious. So the point is we don't need to know what Eve knows, we just need to know that she doesn't know too much. And then we can apply an extractor. And by the way, so these ideas about sort of Eve knowing something, they go back to the 80s, and the first papers people designed were, what if Eve knows this thing? And then what if Eve knows that thing? And slowly they realized the techniques are general enough, but it took a while. And sort of in modern language, it's all trivial. But it took a lot of work to get there, right? And it took a lot of definitions of the right notions. Okay, so now we're going to move to a harder problem, information reconciliation. Information reconciliation is like the previous setting, except life is only a little bit worse in that what Bob has is not actually exactly identical to Alice, but it's somewhat different. Maybe not too different. So if you shake two phones, right, the accelerometers are not going to measure the exact same thing because of calibration issues and orientation issues and whatnot. If you do quantum key distribution, some quantum bits could flip along the way because of, I don't know, cosmic rays or whatever causes quantum bits to flip. I'm making stuff up. Right? And the problem also goes back to Bennett-Broussard. Everything goes back to Bennett-Broussard and Robert. This is like the third time I have to cite this paper, right? They already considered that. Okay, and what do I mean by some metric? For now, let's think of Hamming distance, the number of bit flips. There are more general definitions, but for this talk, I want to think about the Hamming distance. Okay, so how do we do this? There's a generic technique that people have thought about. I'm going to apply some algorithm called S for sketch. S stands for sketch to my W. I'm Alice now. And I'm going to send some error correcting info, S, to Bob. And then I'm also going to extract. So my W is going into two algorithms, the error correcting algorithm and the extractor algorithm. Before it was just extractor, right? Now I'm doing for both. And I send both things, the extractor seed and the sketch, over to Bob. Bob is going to recover W using the error correcting information. I'll show you how to do that in a moment. I'll show you a concrete example of this error correcting information, but not yet. And then this thing will get extracted, and they'll extract the same thing. Okay? So that's the big idea of how to do this sort of thing. Well, how long an R can you extract? That's of course what you want to know, right? What kind of extractor you can use. And how long an R you can extract depends, of course, on the entropy, right? Of what? Of W, condition on what Eve knew before you even started, she knew Y, and what she finds out now, which is also S. So now you've added something, right, to Eve's knowledge by sending that error correcting information. So here's a nice lemma that says that if you condition on a new variable, you're reducing by the bit length of that variable, by no more than the bit length of that variable. So if I'm, which is intuitively makes perfect sense. If I have 100 bits of information that's secret from Eve, and I said 3 bits, Eve ought to have no more than 97 bits. It should be rather, Eve ought to have no more than 3 bits, so I should still have 97 bits of secrecy. So intuitively, it's the right statement. The fact that it's actually the right statement is nice, right? That you can prove it using this.
Sure, we have that S on the right-hand side, the S inside.
Yes.
So it's W is conditional.
In other words, if this information was entirely uncorrelated with W, imagine these, S is 3 bits of information entirely uncorrelated with anything. Then conditioning on it shouldn't reduce the entropy. Yes. And indeed it won't, because it'll increase this side and then it'll decrease this side, and it'll work exactly. I'll show you an example of how this is used. It's actually very nice. Does it make sense? So the entropy of W, when it's conditioned on an additional thing, gets reduced by exactly the bit length of that thing, but increased if that thing was independent of W to begin with. And that holds even if W was initially conditioned. So you can keep conditioning and conditioning and conditioning, and it'll work. So why is this useful? I actually want to show you an instantiation of this protocol and how easy the analysis becomes given this lemma. Right. So I'm going to show you how to build this error correcting information. This has nothing to do with entropy, but it's cute enough, and the analysis will be very nice after that. So I think it's worth it.
Where can I find this lemma?
I don't want to scroll all the way back. It's in the same paper of myself, Ostrovsky, Doris, and Smith, where we define this notion. So we define the notion, prove this lemma. I can send you the link. So let's build this S. Okay, we're going to build it, not surprisingly, out of error correcting codes. And the way we're going to think of error correcting codes, a code is sort of a function that maps n-bit messages into n-bit code words. Okay, that's the way we're going to think of it. So here are all the messages, and this is the entire space of m-bit messages, and this is 2 to the m possible code words in a much larger space of 2 to the n, right? And so they're all far apart. That's the way to think of codes. And any 2 code words will differ in at least d locations. That's the nice feature of error correcting codes, and therefore if you have fewer than d over 2 errors, you know exactly where things came from. Okay, so that's just the background on what I'm going to mean by error correcting code. So how do we then use this error correcting code to actually transmit this error correcting information? Well, what if we know, Alice, I'm Alice, right? So I have my W, right? And you have a W prime. What if you happen to know that my W is a code word? Well, as long as your number of errors, W prime, is not too big, you can just decode to that code word. You don't need any information from me, right? If I have a code word and you have a corrupted code word, decode. We're done. Okay, well, that's not the case, of course, always in life. But what we're going to do is if my W is not a code word, I'm going to shift the entire code to make it a code word. What do you mean by shift? I mean I'm going to take a random code word. This is a random code word, error correcting encoding of a random message. That's a random code word. And I'm going to shift it, since we're in the binary case, it's just XOR, to random W. Sorry, to my W. Okay? That offset is what I'm going to send to you. How do you decode? Okay, so this is what I send you, right? This shift. How do you decode? Let's just forget about the formula. Think about the picture. You have a W prime, right? You shift it back by the offset. You decode, and you shift it forward by the same offset. Shifting back and shifting forward in the binary case is the same thing, so it's all XOR, but logically that's what's happening. Because I've told you here's the offset of the code, and now in that offset code, my W is a code word. So you just have to offset things and work it out. Right? This construction is due to Jules and Wattenberg in 2002, but there wasn't really a nice analysis of it because they didn't have the notions of entropy, right? So there was some analysis of it, but let's actually analyze it the way I want to analyze it, because it all fits onto one slide, and I can prove a very strong thing about it, whereas before we really didn't know how to do that. So Alice does on her own, she extracts R, and she also sends this information over to Bob, a random code word XORed with her W. That's the information. Okay? And we have this lemma that I already showed you, that this is the amount of entropy we have. And now just using this lemma, I'll tell you how big R can be. Okay, so let's think about it. How much entropy do we have? Well, what happened? There was some entropy to begin with, and then there was randomness that went into here. How many bits of randomness went into here? Well, the length of the random thing that we encoded. R was a random value that we encoded to get a random code word. Right, so we took a random R and just applied the error correcting encoding function to it to get. So this was whatever was there originally plus R, because we added that in. And the bit length of S is N. N is the length of our W. N is always the length of our W. So okay, so let's do some more bit counting. This is M, because the code goes from M bits to N bits. This is N. This is it, right? So the entropy of what we have conditioned what Eve has is whatever we had originally plus M minus N. So if you have a good code, then the entropy loss due to this extra step is N minus M. If the code goes from M bits to N bits. So if people give me better codes, I get a better result. I now can hand off the problem to error correcting people and tell them give me good codes. Right? Good codes are the ones where the distance between M and N is not too big, where the encoding is not that much longer than the word. So this is the entire analysis on one slide, right? That's the nice thing. So I know exactly how many bits I can extract, whatever entropy I had initially, minus. Okay. Yeah? I'm going? All right. Sorry?
So the reason you introduce this random code word is that you don't want your secrecy to depend on the distribution of W. Is that true?
Why do I introduce a random code? Right. Well, I don't know the distribution of W, so I have to shift it to. I could also shift it. It's trickier to analyze, but I could shift it to a fixed. No, I can't shift it to a fixed code because that in a linear code I could do other things. But let's not think of linear code.
what if I already know the distribution of W? Do I still need to do this shift?
Yes. A distribution is not enough, right? Because
why is this shift doesn't exist in the original paper on from mirror?
It does, implicitly. You just can't see it, but it's in there. I'll show you offline, but it is in there. They use systematic codes. They use a different trick. They use systematic codes and send over the tail.
Yes.
But it's all equivalent because of duality of error correcting codes. It's the same thing, really. Okay, so let's consider the case of an active adversary. It's everything we've done so far, but now Eve can actually modify the messages between us. Right? That seems trickier. Right, so what we want to say is, look, if we catch Eve doing this, then the best thing we can do is give up. This is sort of like the key agreement talk we had 1 hour ago, right?
Yeah.
And this goes back to Maurer from 97. And notice that this is interesting even if the two things are the same. Because the trick is to get the extractor seed across. If I can get the extractor seed across and make sure Eve does not modify it, then I'm okay. That's really the main trick. Because Eve gets to modify stuff, right? So how do I get it across and make sure I detect modification? And the problem is that we cannot use the only thing we have to begin with is this W. And we cannot use it as a MAC key if it's not at least half entropic. That's what I showed you at the very beginning, that it can be used if it's half entropic, but otherwise it cannot. So what do I do?
That's also only in the case when W is equal to W.
Right. So actually I'm not going to address the unequal case, but essentially you solve it the same way as we solved this previous thing, adding some authentication in. So the idea, due to Renner and Wolf, actually, is to use interaction in order to do this, right? And so since you asked, Shweta, their work was for the case when W is equal to W prime, and then Bhavna and I had follow-up work that made W not equal to W prime, and still made it work. Okay. So I want to show you how they authenticate one bit of the extractor seed, and then you will believe me that they can authenticate the entire extractor seed, because it's just bit by bit. Okay? So how do they authenticate one bit of extractor seed? Bob sends a challenge, and that gets Alice applies an extractor on W to that challenge. This is not the extractor. This is not the ultimate extractor that they want to use. This is just an extractor as a tool. Yeah?
But the adversary could modify this challenge.
Yes. Correct. We'll see exactly what happens. Okay. And then Alice wants to authenticate a bit B, right? So what she's going to do is she's going to send the extracted result if the bit is 1, and otherwise she's just going to send 0 and no extracted result. Okay. And Bob is going to accept if this is correct. So you stare at this for a little bit. It makes absolutely no sense. We'll try to make it make sense in a moment. What Shweta says is that Eve can make Bob's view not equal to Alice's view. Eve is perfectly capable of taking the extractor seed that Bob sent, making it into a different extractor seed. Nothing to stop Eve from doing that. Alice will extract some T prime. And in fact, extractors don't guarantee anything. So she could even take this T prime and modify it to a T that Bob will accept. Eve could do that evil thing, right? But that doesn't concern us. What concerns us is that Eve cannot change a 0 to a 1. What's a 0? A 0 is when Alice sends nothing, and a 1 is when Alice sends something. And all we want to prove is that it's hard to change something to nothing to something, right? So T has entropy. And there is a... Ooh, this thing is acting up. Okay. Wait, where were we? Here we were. To prevent a change from a 1 to a 0, we'll just make the number of zeros equal to the number of 1s. Same trick as 2 hours ago, right? B is a bit. I just want to authenticate a single bit for now. Eventually, I'll want to authenticate a whole long extractor seed I, but I'm going to do it one bit at a time. And so I'm going to only worry for now about changing a 0 to a 1, because in my big extractor seed, I'll make it balanced. And then, so I'm not going to worry about this one. So even though Eve can make the two views unequal, she cannot change logically the bit that Alice is sending. Alice is sending some bit logically over to Bob using this trick. Okay, so how do we prove that?
Wait, sorry.
Uh-huh.
You said that Bob accepts a 1 if the extraction is correct.
Yes, sorry.
Does he just always accept? Like if he gets a 0, does he just...
He accepts, yeah. There's nothing. Yeah, if you see a 0 bit, you go, oh, yeah, thank you for sending me the 0.
Oh.
If you see a 1 bit, you verify that the extraction is correct.
And Eve doesn't know W.
Eve doesn't know W. That's the only thing that Eve doesn't know, right? That's the problem is we're trying to agree on a key from something that Eve doesn't know, and we have to use that something in order to agree on a key. It's a chicken and egg sort of problem, right? Okay. So here's a lemma from a paper by Bhavna and myself. The entropy of the extracted value, this value this value t right here, the entropy of the value t conditioned on everything Eve knows, including x, is sufficiently high. How high? Well, there are two parameters in extractors: the output length and how close the output is to uniform. So if the output is far from uniform, it's not a very good thing. But if the output is close to uniform, then it's exactly as long as the extractor output, -1. Okay? So now what does this lemma give us? This lemma immediately gives us that if Eve sees x and whatever other knowledge she had, as long as W had entropy, this whole thing, this T is going to have entropy. Right? If Eve sees x, then T is going to have entropy. And if Alice is sending a 0, she's not going to respond, so she cannot possibly reduce the entropy. If she's sending a 1, that entropy may get reduced by her response. But if she's sending a 0, the entropy cannot get reduced. So for Eve to guess T is going to be hard. This is interesting. Hand waving causes... there may be a security question here somewhere. So this is going to work. This lemma holds, of course, as long as there's enough entropy in W to begin with. You can't extract something out of nothing. So there's a precondition to the lemma, that W has enough entropy. But we know how much entropy W has because we know how much it has initially, and then we know how much each authenticated bit reduces it. Remember, we're authenticating many bits one at a time this way. But we know how it gets reduced from the previous lemma, that each time you give T bits of information, it reduces by T. So as long as there's enough total, we'll be okay. So this is a very simple analysis of a protocol that did not have such a simple analysis. All right, and the analysis is basically the extracted output has entropy. Listen. Yes. So for every bit, this thing is repeated. This is not a particularly efficient protocol, but this is, I can tell you offline about different follow-up work that makes it better. But essentially, for every bit, I send you a fresh random challenge, you send me a response. Fresh random challenge, send me a response. And then you authenticate the entire extractor seed, which can be logarithmic, so it's not terrible. And then, right? So it's a multi-round thing.
What was the bit about using it to authenticate?
So why are we doing this in the first place? We're doing this because we want to do privacy simplification. And the way we do privacy simplification is by me sending a seed over to you, the seed I, the original seed I. So I'm going to send the seed I over to you by doing this one bit of I at a time. Right, so this is going to, and each time I'm going to come up with this fresh x. And we do challenge response. You see if it's a 0 or 1. You go into the next bit. So we actually have an implementation. It's not terrible. It's, what was it? Well under a second somewhere, right?
I think so.
Or maybe a couple. Well, it's doable. It's not the thing you want to do all the time, but it's doable. If you have no other choice, then it's doable. Okay, I'm probably going to skip this if I want to get a little bit to the computational thing. So Nishant, Bhavna, Rafi, and I have worked on making this protocol more efficient, essentially. And what I wanted to brag about is how easy the analysis is, but I'm going to skip it because it's not so easy. So what about the computational analogues? Everything I've talked about so far is information-theoretic. Why not make computational assumptions and see what we can do with them? I'll try to sketch maybe one or two things very quickly. We'll see how far we get. Okay, so what is the computational analog of Min-Entropy? It's known as Hill entropy. It was defined by Hosted and Pagliazzo, Levin, Luby, as the following thing. a distribution has Hill entropy if it's indistinguishable from some other distribution that actually has true min-entropy. What do I mean by indistinguishable? You take a circuit of a bounded size or Turing machine of bounded time, and it cannot tell the two apart. Right? The usual computational notion. So H Hill of W is greater than or equal to K if there exists a Z that truly has K bits. That's Hill entropy. Okay, you have to be careful now because it got messier because there are two parameters that relate to the indistinguishability. The size of the circuit that you're considering as a distinguisher, right? You have to be computationally bounded, and the distinguishing advantage. There's some probability that it'll distinguish, so that's epsilon. So there's delta and S are the two parameters. Right? There's quality here, quality of distinguishing. So this entropy has quality and quantity. Before, entropy only had quantity. Now it has quality and quantity because it's computational. There's no getting away from those annoying parameters. So what is this one good for? Right? That's sort of the repeated question. Well, basically in any proof where you could use min-entropy, if you have a bounded adversary, you could use Hill entropy, roughly. Because the bounded adversary can't tell that you substituted one for the other because it's indistinguishable. Right? This is a very, very high-level idea, but it works in a lot of places. So for example, right, if you start with a uniform X and you apply a pseudorandom generator to expand it out, what is the min-entropy of the resulting random variable? It's just the length of X. Can't be better. You can't create stuff out of thin air. You can't create entropy out of thin air, right? But the Hill entropy is the length of the output, not the length of the input. So you get a lot more Hill entropy. David?
But there's some others you did previously about min-entropy where you said, oh, if I give you this extra little bit of error-correcting stuff, it only decreases.
Good. You're anticipating 2 slides from now.
Oh, okay.
I'll tell you what dilemmas, what lemmas we can prove about this.
But your notion here about proof substitute Z for W, right? That you can't just substitute that proof in that lemma.
Well, that lemma had I have not yet defined even conditional Hill.
Okay.
Even defining conditional Hill causes some questions.
Okay.
So it's not. Yeah, you're right. You cannot. You're absolutely right. It also turns out that you can apply the good old extractors that we already have. Don't need to redesign them. And if this thing has only Hill entropy and not true min-entropy, then this result will look close to uniform to any circuit that is bounded. It will not actually be close to uniform, but it will look close to uniform. To any bounded circuit, it will not be able to distinguish. That's the sort of the expected thing. Okay. And what about conditional entropy? In real life, entropy is always conditional. If you think about sort of the Diffie-Hellman secret G to the AB, the observer knows G to the A, G to the B. You still want to say that G to the AB has a secret, has entropy, right? That's intuitively what you want to be able to say. There's lots more examples. So how does conditioning reduce entropy? By the probability of condition that we had from before, right? What happens with okay, so these are the examples. Here's a theorem that the same holds for computational entropy, except you get degradation in 2 things. So that's David's question. You get degradation in quantity by exactly what you expect, but also in quality by the probability of the event. So if you're conditioning on a very surprising event, then things go bad, potentially. So degradation happens in 2 parts. And notice that it's the same. It's just that we measure entropy logarithmically and we measure quality not logarithmically. Because there's no log here, but it's actually the same degradation. So both things degrade. So this theorem this formulation is due to Ben Fuller and myself, but it's actually sort of a variant of the dense model theorem. If you've heard of the dense model theorem, then this is cool, and if you haven't, then it's not cool. Sorry?
What's the dense model theorem?
It's actually this result, but in a very different formulation. Then we realize it later, but I'll tell you offline. It's a long story I'm sort of almost out of time anyway. There's one more caveat that we cannot prove this theorem for Hill entropy, which is really unfortunate. We can only prove it for a slightly weaker entropy notion. Given the time constraints, I will not define that entropy notion. I'll just tell you that it's a weaker notion and that it can be converted to Hill. Okay. Actually, I'll fast forward to the slide with the simple message. Simple message is that the lemma I had about information-theoretic entropy also holds for computational entropy. Just for a different notion, but it can be converted to the Hill entropy then. So you can sort of convert back and forth with some losses. Okay. Now again, this is for a specific value y, right? But again, we want to think about an average, right? Not specific Hamming weight, but in general, if you know the Hamming weight, then what? And there's a very nice statement. I will not go here. If y has b-bit strings, then this thing holds. So it's a very clean statement, but again, about a somewhat messier notion of entropy that can be converted to Hill. So now that I've given you all this, let me show you one application and then stop because of time constraints. So what is this whole thing good for? Imagine that we start with a uniform x, we apply a pseudorandom generator, we get a uniform looking w. And imagine now that I'm worried about side channel attacks, where the adversary finds out something about this entire computation, maybe something about x, maybe something about the inner workings, maybe something about w. You know, there's some adversary, that's allegedly a stethoscope, who gets L bits of leakage. And I somehow model the adversary by saying there's no more than L bits of information that the adversary gets. Okay. Well, it's no longer uniform looking. That's pretty clear. But that's not a problem because of my previous lemma that says up to some parameter losses, and I have to fudge here, unfortunately, because of time, that W conditioned on what the adversary sees still has entropy. It just gets reduced by the number of bits of what the adversary sees. Okay? And has Hill entropy. And Hill entropy can be extracted from. We know that from a few slides ago. So we can extract and get a totally uniform looking V. And the nice thing is we notice that these trapezoids have this is bigger than that, right? We can expand X a lot, and then we can extract but not shrink it as much. So we got more bits than we started with. This idea is actually used by a fairly nice result. Maybe you may have heard at least the title. Jimbowski and Piedrzak from 2008 have a result that one of the very early leakage-resilient crypto results, a stream cipher that is resilient against side channel attacks, a certain class of side channel attacks. And the way they model the side channel attacks is by a bounded number of bits of leakage. And this is essentially their proof. I mean, there's a lot more going on in their result because it's trickier than this, but the heart of the proof is this. Except they don't have the nice notions of entropy to work with, and so they don't get the one-slide proof that we have here, right? So this makes it easier. Okay, so that's the moral again. If you have the right notion of conditional entropy and you have the right lemmas, then you get proofs like this, even in the computational sense. Okay, I'm going to skip this part, and I will go to the last slide. Okay. So min-entropy is often the right measure for security, as opposed to, say, Shannon or something else. Conditional entropy we've seen is natural, and a lot of very simple bit counting proofs that you can do. If you leak L bits, then this happens. If you condition on, a secret of this length, then this happens. That sort of thing. It's very simple. But even in the computational case, you can still use it to simplify proofs. And there's lots of open problems. If anybody is interested, talk to me. In the information-theoretic case, we actually have this kind of result. If you started with a conditional entropy, you condition further, you just reduce by the number of bits. In the computational case, I have to start with unconditional in order for this result to hold. So there cannot be a y1. That is, I don't know how to prove it. It's annoying. Should be able to.
Do you have a short way to tell us why?
Yes. Here is a short way to tell you why. I did not pay her this time, really didn't. Sometimes, right, so what is the bad case for us, where the proof breaks down? Imagine that W is a plain text, and Y1 is the public key. Okay? On average, the plain text has some entropy conditioned on the public key, but for any fixed value of the public key, there exists an adversary that has the secret key, and therefore has no entropy anymore. Does that make any sense? So if I give you the ciphertext on the public key, right? The plain text has entropy somehow, logically. But if you happen to know the secret key, then it doesn't. If I fix any particular value of a public key, then there exists an adversary who happens to have the secret key hardwired, right? So for every particular value of y1, I have no entropy. On average, I do. This screws things up because I only know how to deal with specific values of y1. I don't know how to deal with on average. And that is really annoying, actually. So that's the nutshell. It would be nice not to have to go through this weird notion of entropy that I sort of didn't tell you about, but condition H Hill directly and not have to convert. It would be nice to get rid of exponential quality loss that happens here, but only quantity loss. And maybe we need a totally different notion of computational entropy. There's 2 more notions that I skipped in this talk that I could have talked to you about computationally. Nobody knows exactly what the right notion is to make theorems look nice, right? Because that's what the right notion is about. All right, and yeah, that's also open. Lots of definitions. Do we know anything about them? And which one is the right one? All right, thank you.
Any other questions?
Thank you.